I want you to imagine that there are two clocks sitting on the table in front of you. They are identical, same brass case, same glass face, same second hand moving with the same delicate mechanical click. You synchronize them perfectly, 12 o'clock exactly, and then you leave one clock on the table. You place the other aboard a spacecraft and send it racing through space at an enormous fraction of the speed of light. Eventually, the spacecraft returns. You place the two clocks beside each other again. And something deeply unsettling has happened. They disagree, not because one clock malfunctioned, not because gravity damaged the mechanism, not because someone secretly changed the hands. They disagree because the two clocks experience different amounts of time. The traveler may have aged less, fewer heartbeats, fewer chemical reactions, fewer seconds. That is not philosophy. That is relativity. And it immediately destroys one of the most deeply rooted assumptions your brain makes every waking moment. There is no single universal clock ticking behind reality. There is no cosmic metronome giving the same beat to every observer everywhere. Motion matters, gravity matters, the path you take through space time matters. And once you follow that idea all the way down into quantum gravity, something even stranger happens. Time begins to disappear from the equations. I need to be very careful here. Physics has not proven that time is imaginary. Your clock is not lying to you. Events occur, systems change, your body ages, entropy increases, radioactive atoms decay, the universe evolves. But the thing you instinctively imagine as time, a universal river flowing identically through all of reality from a shared past into a shared future, is not what modern physics describes. Relativity fractured that picture. Quantum gravity may fracture it even further. And some physicists now explore a possibility that sounds almost impossible when you first hear it. Time may not be fundamental, it may emerge like temperature, like pressure, like a wave on the ocean, real at the scale where we experience it, but absent from the deeper description underneath. That is the door. And tonight, I want you to imagine what reality looks like if the clock on the wall is not measuring one of the fundamental ingredients of the universe. What if it is measuring something that appears only when pieces of the universe relate to one another? Before we step through that door together, take a moment to subscribe to Deep Field Lecture. If you want to understand the places where familiar reality begins to dissolve into deeper physics, you are in the exact right place. Now, I want you to imagine a railway platform. You are standing beside the tracks. A very long train passes you at tremendous speed. At the center of one carriage, a flash of light occurs. The light travels toward the front of the carriage and toward the back to a passenger sitting exactly in the middle of that carriage. The light reaches the front and rear ends at the same time. Perfect symmetry, but you are standing outside the train. From your perspective, while the light travels, the rear of the carriage is moving toward one pulse and the front of the carriage is moving away from the other. You do not agree with the passenger about which events were simultaneous. Neither observer is making a mistake. This is the relativity of simultaneity, and it is one of the most important clues in this entire story. In special relativity, different observers moving relative to one another can disagree about whether spatially separated events occur at the same time. There is no observer independent universal definition of now stretching across all of space. Hold on to that image because your everyday picture of reality depends on a universal present. You imagine that right now, while you are listening to these words, something is happening on Mars. Something is happening around Alpha Centauri. Something is happening in the Andromeda galaxy. And you instinctively imagine that all of those events belong to the same cosmic slice called now. Einstein tells us that nature does not provide that slice uniquely. Different observers can divide space time into past, present, and future differently. The events remain and the slicing changes. This gives rise to an extraordinary way of thinking about reality. Imagine a loaf of bread. Each slice represents what one observer calls the present. Another observer moving differently cuts the loaf at a different angle. Same loaf, different slices. The loaf itself is space time. And in relativity, space time is the more fundamental structure. Space and time are not entirely separate backgrounds, they are woven together. The distinction between how much of an interval belongs to space and how much belongs to time depends on the observer, but the space time relationship remains. This is why the phrase time is relative is much more radical than it sounds. It does not mean time merely feels different when you are bored. It means different observers genuinely measure different elapsed times between events. Experiments with precise clocks have confirmed this. Satellite navigation systems must account for relativistic effects. Particles moving close to the speed of light survive longer in our frame than they would if they were at rest. Clocks at different gravitational potentials tick at different rates. Reality does not own one master clock. Each path through space time carries its own proper time. Now, I want you to really grasp what this means. Imagine two twins. One stays on Earth, one travels through space at enormous speed and returns. The traveling twin can be younger. This is not because time itself slowed down in some universal external dimension, and the two people traveled along different paths through space time. Those paths contain different amounts of proper time. The clock is not malfunctioning. The universe is geometrical. Hold on to the two clocks because we are about to break them open. General relativity takes the story further. Gravity, Einstein taught us, is not simply an invisible force pulling objects together. Mass and energy curve space-time. Objects move through that curved geometry, and clocks are part of the geometry. Place a clock deeper in a gravitational field and it runs differently compared with a clock farther away. Near an extremely compact object, such as a black hole, the difference can become enormous when compared between observers following different paths. Again, there is no universal tick, and there are local clocks, local measurements, and local histories. Already, the everyday idea of time has begun to dissolve, but the universe, as I've learned time and time again, has a deeply humbling sense of humor because relativity still contains space time. Time has changed its role, but it remains part of the geometry. Then we try to combine gravity with quantum mechanics, and the clock vanishes. To understand why, I want you to imagine two books. The first book is Quantum Mechanics, the second is General Relativity. Each is extraordinarily successful. Each describes nature with astonishing precision, but they treat time very differently. In ordinary quantum mechanics, time behaves like an external parameter. A quantum state changes with time. The Schrödinger equation tells us how you give the theory a clock. The quantum state evolves according to that clock. General relativity does not treat time this way. There is no universal external clock sitting outside space-time. Time is part of the dynamical geometry itself. Matter changes geometry, geometry changes motion, and the stage participates in the play. Now try to quantize the stage. This is where the problem begins. In one major approach to canonical quantum gravity, physicists encounter the Wheeler-DeWitt equation, and when written in its famous form, there is no ordinary external time variable telling the wave function of the universe how to evolve. So the universe appears mathematically frozen. This is known as the problem of time in quantum gravity. Modern reviews emphasize that the normal route to a time-dependent Schrödinger equation is not straightforward once space-time geometry itself becomes quantum mechanical. Think about how strange that is. We build quantum mechanics around evolution. A state at one time becomes a state at another. But when we apply the framework to the entire universe, there is no external clock left. What could the universe evolve relative to? There is nothing outside the universe holding a stopwatch. The watchmaker has disappeared. Here is the hard truth. Our most successful theory of gravity and our most successful framework for microscopic physics do not naturally agree about what time is. This is not a small technical inconvenience. It may be telling us that our everyday concept of time belongs to an approximate layer of reality. And imagine a photograph. Everything in the photograph exists at once. And the river, the tree, the person walking, the clouds, there is no motion inside the photograph itself. Yet, if the photograph were one frame in a larger sequence, an observer could recover change by comparing relationships between frames. Now imagine something even stranger. There is only one enormous quantum state, no external sequence, no cosmic movie projector, and yet some parts of that state can function as clocks relative to other parts. Change emerges internally. This brings us to one of the most fascinating ideas in the physics of time. I want you to imagine two pendulums in a sealed box. There is no clock outside. You are not allowed to say that 1 second has passed, but you can still say something relational. When pendulum A reaches this position, pendulum B is there. When A reaches another position, B has moved. One subsystem becomes the clock for another. Time becomes relationship. Hold on to that image. In the Page-Wooders approach, first proposed decades ago and explored experimentally and theoretically in later work, a global quantum state can be stationary while observers using part of the system as a clock recover an effective evolution. For the rest, modern research continues to investigate how temporal behavior can emerge through quantum correlations between subsystems. This does not prove that time is produced by entanglement, but it demonstrates something conceptually extraordinary. A world that appears static from one mathematical perspective can contain observers who experience change internally. The universe can be timeless globally and temporal relationally. The coin is rigged. Our intuition says change requires an external time coordinate. Quantum theory suggests that correlations themselves may be enough. Imagine opening a novel. Every page already exists. Page 1, page 100, page 300. The characters inside the book do not move physically from page to page, yet the relationships written across those pages define a sequence: cause, memory, expectation, development. An observer inside the story experiences a narrative, even though from outside, the whole book may be treated as one object. This metaphor leads naturally to something often called the block universe. In relativity, space-time can be represented as a four-dimensional structure containing events. Your birth is an event. Listening to this sentence is an event. Tomorrow morning is an event. From this perspective, the universe is not necessarily a three-dimensional world continuously being rewritten by a moving present. It is a four-dimensional geometry. The past and future appear differently in our experience, but the equations do not contain a universal spotlight labeled now moving through space-time. Relativity itself does not force every philosophical interpretation of the block universe, but it does remove the absolute simultaneity that our naive picture of a universal present requires. This is where your intuition is going to completely fail you. And it should. Your brain did not evolve to understand space time, it evolved to survive. A nervous system needs to remember where food was, predict where a predator will move, coordinate muscles, identify cause and effect, separate memory from anticipation. A strong psychological distinction between past and future is useful. It may even be unavoidable for a creature like us, but usefulness is not fundamentality. Color feels fundamental, yet color is your brain's interpretation of electromagnetic wavelengths. Temperature feels fundamental, yet temperature emerges statistically from microscopic motion. Pressure feels fundamental, yet pressure arises from enormous numbers of particle interactions. A wave seems like an object moving across water, but the water molecules mostly oscillate locally. The wave is a collective pattern. What if time belongs in the same category? Not unreal, emergent. I want you to imagine a glass of water. You ask for the temperature, 20 degrees Celsius, perfectly meaningful. Now isolate one individual water molecule, ask for the temperature of that molecule. The question begins to lose its usual meaning. Temperature belongs naturally to the collective system. It emerges from statistics. Perhaps time works similarly. At the scale of human beings, planets, stars, and laboratories, temporal evolution is indispensable. But at the deepest quantum gravitational level, perhaps there is no fundamental variable corresponding to the universal time we imagine. Instead, there may be configurations, correlations, causal relationships, entanglement, geometry, and when enough of these ingredients organize themselves in the right way, something behaving like time appears. Some semi-causalistic approaches to quantum cosmology explore precisely this possibility. An effective time parameter can arise when portions of a quantum gravitational system behave approximately classically, allowing matter fields to obey a familiar time dependent equation. The clock emerges from the system. The universe does not evolve inside time. Time emerges inside the universe. I want you to sit with that sentence because it reverses nearly everything intuition tells you. We normally imagine the universe as objects placed inside space and evolving inside time. But modern fundamental physics repeatedly suggests that space and time themselves may need explaining. They may not be containers, they may be consequences. This idea appears in several approaches to quantum gravity, though no single framework has been experimentally confirmed as the final description. And that qualification matters. We do not possess a completed experimentally verified quantum theory of gravity. We do not yet know whether time truly emerges from entanglement, geometry, thermodynamics, or some deeper structure we have not discovered. The mathematics points toward a problem. The solutions remain under construction, but the problem is real. And now something massive and unknown is swimming in that dark ocean, the arrow of time. Even if time exists as a coordinate, why does it seem to move in only one direction? Why do you remember yesterday and not tomorrow? Why does a broken glass not spontaneously leap from the floor and reconstruct itself on the table? Why does smoke spread through a room but never gather itself neatly back into the cigarette? Most fundamental microscopic laws do not contain the strong everyday asymmetry we experience between past and future. Yet our lives are dominated by it. We are born, we age, we remember, and we die. Entropy gives us the central clue. I want you to imagine a new deck of cards, perfectly ordered, all suits grouped, all numbers arranged. Now shuffle it. There are vastly more disordered arrangements than ordered ones. Shuffle again and again. The deck almost never spontaneously returns to its precise original configuration, not because the laws forbid it, because the number of disordered states is overwhelmingly larger. Entropy tracks this statistical tendency. In a closed system, entropy tends to increase. That gives physical processes a direction, a thermodynamic arrow, and the past corresponds extraordinarily to lower entropy, and the future generally corresponds to higher entropy. But this immediately produces another mystery. Why was the early universe in such a special low entropy state? The Big Bang was hot, but gravitational entropy behaves in subtle ways. The early universe was remarkably smooth. Matter had not yet collapsed into the enormous gravitational structures we see today. Stars, galaxies, black holes, the universe began in an extraordinarily special configuration, and our arrow of time may ultimately trace back to that boundary condition. In other words, the sensation that time flows forward might not be a fundamental flowing property of time at all. It might be connected to the direction in which entropy increases. Here is the hard truth. Physics contains several different concepts that everyday language collapses into one word: time as measured by clocks, time as a coordinate, proper time along a trajectory, and the thermodynamic arrow, psychological time, causal order, quantum evolution, cosmic time used in cosmology. They are related, but they are not identical. When someone asks, does time exist? The first task is to ask which time they mean. The clock on your wrist measures something real. Relativity predicts its behavior with extraordinary accuracy, but the flowing universal present you feel may be partly a construction of perspective, causality, memory, and thermodynamic asymmetry. You may not be moving through a cosmic river. You may be a physical system tracing a path through spacetime while carrying records of lower entropy states. That sentence sounds cold, but its implications are deeply personal. Look around the room you are sitting in right now. Your brain contains memories. Those memories are physical structures, neural states, chemical arrangements, information stored in matter. You have records of yesterday because yesterday left physical traces, photographs, scars, documents, changes in your brain. The past is full of records. The future is not. Perhaps that is why the past feels fixed and the future feels open, not because one ontologically exists and the other does not in some simple sense, but because information is distributed asymmetrically. You are a memory forming machine embedded in an entropy gradient. Your experience of time may be inseparable from the kind of physical system you are. This is where the question becomes almost existential. If the block universe picture is useful, is your future already there? The equations alone do not give us a simple answer to everything philosophers mean by that question. But relativity makes the ordinary idea of a universal moving present difficult to sustain. Different observers disagree about distant simultaneity. What one observer calls now is not a privileged slice written into nature for everyone. So perhaps the universe does not continually manufacture reality moment by moment. Perhaps events belong to space-time, while our consciousness experiences them sequentially along a world line. Think of a piece of music. The entire score can exist on one page. Every note is written, yet the listener hears the symphony in sequence, first note, and then another, and then another. Meaning emerges from the relationships across the sequence. Perhaps consciousness is similar. The score is space time, the melody is experience. You do not hear the entire symphony simultaneously because your brain is a local physical process. It processes information in ordered states. The experience of passage may belong to the performer rather than the paper. But now I want to push the metaphor further. At the deepest quantum level, perhaps even the score is not fundamental. Perhaps relationships between notes produce the page. This is where quantum gravity becomes genuinely strange. Some research programs suggest space-time geometry itself may emerge from deeper quantum degrees of freedom. Entanglement has become especially important in modern discussions of how geometry and quantum information might be connected. If space can emerge from deeper relationships, then perhaps time does too, not as an independent substance, as structure, a relationship between changing parts, a way one subsystem measures another. This possibility is still speculative at the fundamental level. No experiment has shown that the universe literally consists of timeless quantum information from which space time uniquely emerges. But the direction of research tells us something important. Physicists no longer universally treat space and time as unquestionable foundations. They are problems to be explained. Think about the sheer weight of that. For thousands of years, time was the background against which everything happened. Galileo measured motion through time. Newton imagined absolute time flowing uniformly by itself. Einstein shattered absolute time and fused it with space. Quantum gravity now asks whether even space time is secondary. So the progression is remarkable. First time was absolute and then relative, now perhaps emergent. Each step removes another piece of human intuition from the foundation. Newton would have imagined a universal clock. Einstein showed us that no such clock exists. Quantum gravity may show us that clocks themselves arise from deeper correlations. Now it is our turn. What would it mean if time is emergent? It would not mean your life is fake. A hurricane is emergent, still real. A wave is emergent, still capable of destroying a ship. Temperature is emergent, still capable of burning your hand. Emergence does not mean illusion. It means a phenomenon becomes meaningful at one level, even though it is absent from the most microscopic description. If time is emergent, then birth and death remain real events. Aging remains real. Causality remains meaningful where the theory supports it. Your memories remain yours. What changes is our metaphysical picture. Time would no longer be the stage on which the universe performs. It would be part of the performance. And perhaps this is why attempts to quantize gravity struggle so deeply with it. We keep trying to place the universe inside a clock that belongs to the universe. Imagine asking where Earth is located without allowing yourself to refer to anything outside Earth. You need relationships, latitude relative to an axis, position relative to other bodies. Perhaps time ultimately works the same way, not what time is the universe in, but what is one part of the universe doing when another part has this configuration. Relational time, one clock compared with another, one field compared with another, one state correlated with another. There is no need for an invisible cosmic hand sweeping across reality, only change relative to change. The pendulum becomes the clock because something else changes with it. Hold on to that image. Two pendulums in a dark box, no wall clock, no external observer. One swings, the other changes, and from the relationship, a history appears. Perhaps the deepest question was never why time flows. Perhaps nothing flows. Perhaps physical systems change relative to one another. Entropy gives those changes an arrow. Memory gives that arrow a psychological direction. And consciousness names the result time. That is not established fact, but it is a possibility serious enough that modern physics cannot ignore it. And if it is right, the world around you becomes stranger without changing appearance at all. The clock still ticks, morning still comes. You still remember yesterday, you still anticipate tomorrow, but underneath that familiar sequence may lie a reality with no master clock, no universal present, and perhaps no fundamental time variable at all. Journeys like this, deep into the bleeding edge of human knowledge, require time, deep focus, and a relentless distinction between established physics and ideas still being tested. Below this video, you will see a button labeled Super Thanks. If you choose to support the channel there, you help make these long-form explorations possible. But before we end, I want you to return to the images we carried through this journey. The two clocks taught us that elapsed time depends on the path through spacetime. The moving train taught us that observers can disagree about simultaneity. The loaf of bread showed us spacetime divided into different slices of now. The two books exposed the conflict between quantum theory's external time and relativity's dynamical spacetime. The frozen photograph introduced the problem of time. And the two pendulums showed us how change can become relational. The shuffled cards gave us the arrow of entropy. And the musical score reminded us that a complete structure can still be experienced sequentially from within. We have not proven that time does not exist. That sentence would go too far. And what physics has shown is more subtle. The universal time Newton imagined does not exist. There is no single cosmic now shared by every observer. Clocks follow space time. Gravity changes their relationships. Motion changes their relationships. And at the frontier of quantum gravity, the very equations meant to describe the universe as a whole confront us with a profound problem. Where did time go? Perhaps the answer is that we have been searching at the wrong level. Perhaps time is not written into the deepest foundation. Perhaps it appears when one part of reality becomes a clock for another. Perhaps entropy gives it direction. Perhaps memory turns direction into experience. Perhaps consciousness turns experience into flow, and the door remains open. And behind it is a possibility more disturbing than the idea that time eventually ends, the possibility that the thing we call time was never a river carrying the universe forward at all. Maybe the universe simply is, and the feeling of moving through it belongs to creatures like you and me.